Let's determine the point group of hydrazine, H4N2. So what does hydrazine look like? We have a nitrogen singly bonded to another nitrogen, and each nitrogen is singly bonded to two hydrogens. So we have nitrogen with 3 sigma bonds. Each nitrogen also has a lone pair. So this is the structure of hydrazine. This structure on its own looks planar, which is inaccurate. So we have 3 main conformations. Conformation 1 is eclipsed, also known as cis-hydrazine. On this structure, we have the nitrogen in the front with its sigma bonds to hydrogens overlapping with the nitrogen in the back. This is a molecular model of the cis-hydrazine. You can see we have the 2 nitrogens aligning and the bonds align, and then the lone pair is going to sit somewhere above each of these nitrogens. Next we have the Gauche conformer. The Gauche conformer has the same front face as the eclipsed or cis, but then what we're going to do is take the back nitrogen and rotate it so it's like this. So you can see that effectively it's perpendicular. If we were to take the lone pair here and take the lone pair in the back, one is, sticking to the left and one is sticking to the right. It's perpendicular to each other. Finally, if we twist all the way into the anti or trans conformation, we'll have this. And in this case, we have 2 hydrogens on the back nitrogen sticking up, and on the front nitrogen, they're facing down, and the lone pairs are facing up and down on their respective nitrogens. So that's the anti or trans conformation. Let's begin with the point group of eclipsed or cis-hydrazine. So we'll be using this point group flowchart. So the first question after start asks, is the molecule linear? It's not linear, and we know that because the linear ones are the ones that have an infinite rotation axis. So no, not linear. Then does it have 2 or more CN axes with n is greater than 2? Remember, the CN axis is a rotation axis, and if n is greater than 2, then what that means is that we can rotate it less than 180 degrees and it will look the same. Because remember, CN, the n comes from 360 degrees divided by n. So if n equals 2, then you can rotate it by 360 degrees divided by 2, which is 180 degrees, and it will look the same. Or if it's 3, then 360 divided by 3, which is 120 degrees, and the molecule will look the same. So that's where the n comes from. We do not have that. The next question says, do we have a CN axis? This is an axis of rotation. So effectively, can we draw a line through the molecule and rotate it about that line with n has to be greater than 1? Well, let's look at this molecule. Is there anywhere where we can draw a line and rotate through? We can draw a line right through the center here and rotate about this line 180 degrees. And that gives us the same orientation of the molecule. So we do have a C2 axis through the center of the molecule. Are there n C2 axes perpendicular to the principal axis? So the principal axis is the C2 we just identified, and I do not see any more C2 axis on this molecule, so the answer is no. Now, is there a horizontal mirror plane? The horizontal mirror plane is a mirror plane perpendicular to the C2 axis. So if we draw a molecule and we have a C2 right there facing down through the molecule, the same as we have here, then we'll assign this axis the z-axis. So the z-axis is where the principal axis is. Now horizontal will be defined as in the xy plane. So it's perpendicular to this z-axis. So can we reflect across the xy plane and have the molecule look the same? In this case, we cannot, because if we do that, then the molecule will actually flip and look like this, which is not the same. Now, are there any vertical mirror planes? Vertical mirror planes are mirror planes that go through the principal axis, the z-axis. So if this is our reference right here, then we can say that we could have a vertical mirror plane going through the xz axis, which will be through here, and the yz axis, which will be through here. You could assign x and y to whatever orientation you want in this case, but these are coming up through the z-axis and through x and y. So do we have those? Well, if this is our z-axis right here, then we can draw a plane through here and reflect across, and it will look the same, and the same through here. So we do have two vertical mirror planes. So what is the point group of this molecule in that case? Because we answered yes. C and V, and since N on the CN axis is C2, then that means that the eclipsed or cis hydrazine is C2V. Now let's take a look at gauche hydrazine. So with gauche hydrazine, we can see that we have the lone pair on the front perpendicular to the lone pair on the back. This lone pair is here, and this lone pair is here. So let's use the flowchart again. So is the molecule linear? No, it is not. Do we have two or more CN axis with N is greater than 2? So on this molecule, there's only one CN axis, if you're not considering C1, which is doing nothing. So N is not greater than 2 for that axis, and you can look for a while, and it's hard to find even the individual C2 axis, but it's there. But there's no other ones with N is greater than 2. So does it have a CN axis? Yeah, we have one C2 axis. Where is this? So if we hold the molecule like this, okay, and we draw a line basically through the middle of the bond, then we can rotate 180 degrees. And as you can see, we get the same molecule. So the axis is through, let's just say if we were to hold the molecule so that the bond is like kind of horizontal to each other, then we could draw the C2 axis right through the center. So the C2 will be right through here. Now, do we have N C2 axis perpendicular to the principal C2 axis? No, because we only have that one C2 axis. And then, is there a horizontal mirror plane? Earlier we discussed what a horizontal mirror plane is, and you can see, based on the positions of the back hydrogens, that if we reflect through the XY plane, they'll come up in the front, or in the top, I should say. So there is no horizontal mirror plane. Are there any vertical mirror planes? If we were to reflect across here, these hydrogens would come out on the other side, here, and we cannot reflect across here, because then the hydrogens here will come out right there. So effectively, there's not a vertical mirror plane. no matter which way you rotate it. We cannot find it. And then, is there an S2N axis? So what is S2N axis? This is an improper rotation axis. So what does the improper rotation axis look like? So let's take this system, which looks like trans-hydrazine, where we have two center atoms, and each center atom has two pendant or substituent atoms. On the left one, they're facing down, and on the right one, they're facing up. So what we can do is take a C-axis, like a CN axis, a rotation axis, and we're going to rotate the molecule around that axis. So in this case, I'll draw it through the two center atoms, which could be anything. So like this, so we have a C axis, and in this case I'll draw a C2 axis. Now we're going to take this new structure and we're going to make a sigma axis, a mirror plane, through a spot that's perpendicular to the C2 axis or the rotation axis. So I will take this line drawn between these two center atoms as the mirror plane, and will reflect the molecule across the mirror plane. So as you can see, after conducting that operation, we have a new molecule that looks like the original molecule in the same orientation. Now I'll show you an example using a molecular model kit of trans-hydrazine. So it looks like this. We have two substituents on the first nitrogen facing down, and on the second nitrogen they're facing up. So if we were to rotate this 180 degrees through the NN bond, we'll now have a structure that looks like this one. And now if we're going to take the mirror plane that we drew through this bond perpendicular to the rotation axis, and we flip it across the mirror, which is effectively doing this, we get the same starting molecule. So the question says, is there an S2N axis? We know that N is equal to 2 because our C2 is our primary axis. So do we have an S4 axis? 2 times 2 is 4. That means rotating it 1/4 and then reflecting it over, and we can see that we do not have that. So there is no S2N axis. So the point group is Cn. In this case, the principal axis or the highest order axis is the C2 right here. So the point group of Gauche hydrazine is C2. All right, finally, let's evaluate the point group of anti or trans-hydrazine, which looks like this. So, using the flowchart, is the molecule linear? And the answer is no. Does it have two or more CN axes with n equals 2? So we do have one CN axis, it's a C2 axis, and it goes right through this sigma bond. So if we pick up the molecule and rotate it by 180 degrees, it looks the same. So that's our one C2 axis. Do we have any other axes? No. So do we have two or more CN axis with n is greater than 2? The answer is no. And do we have a CN axis? Yes, we have that one C2 axis. So as we did with the earlier structure, I'm going to draw it like this. And this is where our C2 axis is. Now, are there perpendicular axes? We already said there's no more CN axes where n is not just equal to 1. So the answer is no. Is there a horizontal mirror plane? So if our CN axis is through here, then this is our horizontal plane, slices the molecule in half like here. And in this case, if we reflect across the XY plane, which is like through where my fingers are, so like through here, we do actually have a sigma horizontal mirror plane. If we reflect there through the XY, then the molecule will look the same. So yes, there is a horizontal mirror plane. So since C2 is our greatest axis or highest order axis, and we have a horizontal mirror plane, the point group of anti or trans-hydrazine is C2H.